In chapter 17, we really get stuck into some calculus. So just a few things to go through before we get stuck into 17a. Rates of change. So in the gradient investigation in chapter 16, or as part of chapter 16, we looked at different rates of change of a function. And remember, what we could calculate was the average rate of change, which was the gradient of the secant between 2 points on a function. So remember, what we were choosing is 2 points and calculating the gradient of the secant. And recall that the average rate of change, if this function is f of x, and this point here is, let's just say for argument's sake, a, and this point here is b comma f of b, and a comma f of a, is simply y2 take y1 over x2 take x1. So f of b take away f of a over b take a. Now, what we finished up looking at was the instantaneous rate of change, okay, and that's the more interesting one. The average rate of change is a little bit, I don't know, average, okay? What does that tell us, the average rate of change? I want to know exactly what's happening to a particle or whatever it is we're looking at any given point in time at exactly that point in time, right? So that was the instantaneous rate of change. And what that was the gradient of the tangent to the function at that point. All right, so if I again look at a parabola for argument's sake, and I'm investigating the instantaneous rate of change at this point, if I drew a tangent along there and hit that line there at that point, it'd be the gradient of this line here. That's the instantaneous rate of change at that point. And we can also determine the instantaneous rate of change at a particular point by determining the gradient of the secant as the horizontal distance h between the 2 points approaches 0. That is, that if I want to get the instantaneous rate of change there, what I could do is start there and choose another point and start moving that point closer and closer and closer to this point here, so that I'm working out the difference or the gradient between 2 points, but this second point is getting increasingly close. Okay, so that's what this one here is saying. Determine the gradient of the secant as the horizontal distance h between the 2 points approaches 0, i.e. gets increasingly close. Now we can say this. So as h approaches 0, as the horizontal distance approaches 0, that's this thing here, the gradient of the secant approaches the gradient of the tangent. I meant to write approaches there. So if you see this arrow here, you need to replace it with the word approach. So as the horizontal distance approaches 0, the gradient of the secant approaches the gradient of the tangent. And what we get, the net result of that process, is the instantaneous rate of change. So in the investigation, we approximated instantaneous rate of change of a function. What we'll do is we'll approximate this one here at x equals 5. All right, so we've got x is equal to 5 on the function, and there's another point q here, which is 5 plus h units away from it, i.e. I don't really know how far. So what we could do is just work out the average rate equals, and here we've got y, so we're going to go let f of x, so I want to use some function notation, equals 0.8 t squared. It can't be called f of x there, so I'm just going to replace that with f of t. And I'm going to choose a point incredibly close to 5, that is f of 5.001. Take away the point itself, which is f of 5, over 0.01. That, take away that. What that will do is give us a pretty good approximation of the instantaneous rate of change. So recall that we have been defining our function 0.8 x squared, and okay, so average rate of change between 5 and a point incredibly close to it, 5.001, is 8.0008, whatever the unit is. So units per unit there. So what do you think the gradient will be when the value of h gets closer and closer and closer to 5? Want to take a punt? Well, the answer, I believe, is it's going to get closer and closer and closer to 8. Let's just see what happens. I'm going to drop another couple of zeros there and a couple of zeros there. 1, 2, 3, 4, 2, 3. Okay, so getting closer. All right, so getting closer and closer and closer. And it's only actually hit 8 itself there because of rounding, and the calculator just can't process these. But we can actually say the following. As h approaches 0, so as the horizontal distance approaches 0, that is, that h value there is 5 plus, just getting extremely close to the value 5. As it approaches 0 distance from 5, we say the gradient of PQ, the gradient of this line here, because remember, Q is getting closer and closer and closer as the h distance, it's getting closer and closer, is 8, okay? i.e. the gradient of a tangent drawn at this point here will be 8. The gradient of that line will be 8. All right, so let's get into some language here. So we're going to really hit two new things here. One is called the derivative. Okay, so we'll talk about what the derivative means in a sec. But to work out derivatives, we need to start with what we call limit notation. So here we've got a graph of f of x equals 2 to the x plus 3. That's that graph there. As the x values approach negative infinity, what do the y values approach? So x is approaching negative infinity, the y value is tunneling down, and we're going to say that it approaches 3. All right, the above can be written in limit notation. So what we do is we use this word limit. Okay, so this is lim here. Lim means limit. As x approaches negative infinity, the function f of x or y tends to the value of 3. All right, so basically it's saying that the lower these values get, the closer the function is going to get to the y value of 3. Let's just see how that works. So I'm going to define my function again because I just love defined functions. F of x equals 2 to the x plus 3. And I'm going to do f of, I don't know, negative 2. All right, there it is, 3.25. F of negative 3, getting closer, negative 5, getting closer to 3. F of negative 100. Ooh, that shouldn't have happened. Right, f of negative 10, okay, is somewhere down here. F of negative 20, getting closer. F of negative 30, getting really close. F of negative 40. Whoop. It seems to suggest it hits 3. Now, can I tell you, folks, it doesn't. Okay, so the problem is the calculator can't really process 2 to the power of negative 40. I mean, that number is just insanely big, right? But what it is it's going to be 2 to the negative 40 plus 3, which is 1 over 2 to the 40 plus 3, right? Now, that number is excruciatingly small because 2 to the power of 40 is massive. 1 divided by a massive number is an extremely small number, plus 3. Does it equal 3? No, it does not. Okay, so watch out for the calculator here. It's wrong. It can't process numbers this big. Okay, but we're going to say that the limit as x approaches negative infinity, the y value will become or get closer and closer and closer to the value 3. Not equal to 3, but closer and closer and closer to 3. All right, so let's just try some out. The limit of this function here, or this expression here, as h approaches 0. So that means we're going to say that h gets extremely close to 0. So let's do 22x squared. Now, h approaching 0 is going to have no effect on this term here. What about on this term? As h gets extremely close to 0, it's going to be 0 multiplied by this amount here, which let's just call a spade and say that's going to become 0. As it gets closer and closer towards 0, it's going to essentially become 0. Plus h, which h is approaching 0, we're going to say it's plus 0, which means we're going to get 22x squared. What about this one here? All right, so it looks like you're going to get a divide by 0 error, but what I'm going to suggest to you is let's just maintain h approaches 0, and let's just factor out the h on the numerator. 3x squared plus 2h all over h. Cancel those h's out, and now we're going to apply the limit. Okay, so the limit as h approaches 0 has no effect on that, so that's still 3x squared plus 2h, and as h approaches 0, that's two lots of essentially what is 0, which means we're going to have that or 3x squared. Calc does limits, so you can hit it from Math 3 template. Hardly ever use them, so would have written that a few years ago. Math 3 lim template. It's not even Math 3, it's Math 2. All right, so Math 2 is where that's at. Right, and all you do is you put your limit in as whatever it is approaches. So h approaches 0, type in your expression, 22x squared plus 20x h plus h. And it knows as well to limit h towards 0, so that's pretty much going to knock out that term and that term. So let's apply the concept of the limit to the following example. Calculate the gradient of the tangent to the curve f of x equals x squared at the point 3, 3. So we want to get the gradient of the tangent of that function. So the function is y equals x squared. Try that again. Better. At the point 3, 3. Well, that's wrong. That should be 3, 9. There. Right, so calculate the gradient of the tangent to the curve there. All right, so basically a line's going to run along there, hit it, and we want to get the gradient of this line here, m equals, I don't know. Right, to approximate the instantaneous rate of change, we've been using this clumsy method here of f of 3 and f of 3.001. However, this is still the average rate of change. Okay, it's not instantaneous. Okay, so instead of approximating, which is a bit dodgy, let's try something different. Calculate the rate of change at the point 3, 9 by finding f of 3 and f of 3 plus h, where the limit as h approaches 0. So what we're doing is calculating the average rate of change between a point, which is x is equal to 3, and x is equal to 3 plus h. So we're taking a point at x equals 3 and x equals 3 plus h and sending the limit towards 0. That is, we want there to be no difference between this point here and this point here. Okay, so here's how we write this down. What we're going to do is we're going to say the limit as h approaches 0, and then we're just going to work out the gradient of a line drawn between 3. So we're going to go f of 3 plus h, take away f of 3. So this will be y2, and this will be y1. Okay, f of 3 is 9, over 3 plus h, so that's the x value, 3 plus h, and our other x value, take away 3. All right, so let's see what happens when we do this. So we're going to go limit as h approaches 0. What is f of 3 plus h? Let's slam 3 plus h into f of x. That's going to be 3 plus h all squared. Take away f of 3, which is 9, all over 3 plus h take 3 is just h. All right, now let's go limit as h approaches 0. 9 plus 6h plus h squared, the perfect square expansion. Take away 9 over h. They both cancel out. Haven't used my limit yet. I'm going to pull out h as a factor. 6 plus h squared over h. Now, those cancel out. Now we're left with 6 plus h squared. Now I'm going to throw the limit in there, which means that 0 squared is going to be 0. 6 plus 0 is 6. Therefore, instantaneous rate of change of f of x at x is equal to 3 is 6. That's instantaneous rate of change, or the gradient of the tangent at x equals 3. Right, now I'm just going to use the approximation method and see if that's the case. So f of x is my function x squared, and I'm going to use shift divide f of 3.0001 take away f of 3 over 0.1234. All right, so there's the approximation, 6.00001. This method of selecting a point which is 3 and f of 3 plus h, a point h distance away from 3, and limiting that h value or the distance to getting it to approach 0, allows me to get the exact instantaneous rate of change. It's no longer like, oh, it's pretty much approaching 6. It is 6. Wouldn't it be interesting to be able to calculate the instantaneous rate of change for any value of x for the function f of x equals x squared? Well, I think so, because that would be a new function, and what that would tell us is the instantaneous rate of change for any value of x. This one here is specifically for x equals 3. We're working it out at the point x equals 3. And we know that the gradient is 6, so the instantaneous rate of change is 6. All right, but what about if I could work it out anywhere along here? All right, so we're going to do that right now. So what we're going to do is we're going to say that we've got a point here. So we've got a point x and a y value, which is f of x, all right, and another point, x plus h, and f of x plus h. So what have I done here? I've taken a point x and another point, h distance away from x. And what I'm going to do is say where h approaches 0. Let's let that horizontal distance get closer and closer to 0. All right, so let's do this. So what we're going to say is, and just watch my notation here. I'm just going to write this down and I'm going to explain what I've done here. So we're going to write that down, so pop that into your notes, okay? And we're going to say the limit as h approaches 0. You go f of x plus h, take away f of x. That's y2, y1, x2, x1. Okay, so we've got x plus h, take away x. All right, so let's do this, and again, I'll explain what that means in a bit, but this part here is pretty much, well, not pretty much, it is what we did at the point x is equal to 3, but this time we're just choosing x is equal to x. All right, so let x approach 0, and now let's slam x plus h into our function. Remember, our function is f of x equals x squared. So we're going to do x plus h all squared, take away x squared all over h. The limit as h approaches 0, x squared plus 2xh plus h squared, take away x squared all over h. Those two will cancel out, leaving us with the limit as, no, I'm going to use my limit now actually. No, I'm not. Limit as h approaches 0. Pull out h as a factor on the numerator. Those cancel out. Use my limit now. So I'm going to let h approach 0 in this expression, which will leave me with 2x. Okay, so what we have produced in this instance is what we call the gradient function. So this is what this function is here. I've created a new function called the gradient function. It's also called the derivative function. Okay. The reason why we call it a derivative is it's derived from the original function. There's a relationship between f of x and the function we've produced. And the derivative of f of x is written as f dash x. So we say the derivative of f of x is f dash x. So here's the original function. We call this sometimes referred to as the parent function, f of x equals x squared, down to this function here, f dash x equals 2x. And what you can do with this function is the coolest thing. You can ask it questions just like this. Now remember, this one here, when you drop values of x into the function, it tells you the value of y. Okay, that's what it does. So on the graph, it'll say, all right, when x is equal to 3, the y value is 9. So 3, 9. This function is different. What this does is it is the gradient function, and it will spit out the instantaneous rate of change or the gradient of the tangent for any value of x. Now we've found one earlier. We know that the gradient of the tangent at x equals 3 is 6. So if I did f dash 3, the answer should be 6. 2 times 3, wow, it's 6. And what you can do is sub in any value, f dash 5, that's going to be 2 times 5. The gradient at x equals 5 is 10. Now, if this is a parabola, right, the gradient on this side, the gradient of the tangent on this side should be negative. So if I drop negative 2 into my derivative function, I should get a negative gradient. Hell yeah, I do. Okay, so what we've found there, that is called the gradient function f dash x. Okay, and that's no notation. And more generally, the derivative is defined by this thing here, okay? And I've said here, don't be scared of it. It's basically the same thing as the gradient function, okay, or the gradient formula. So finding the derivative using this method is called first principles, and ask any calculus student about using first principles to find a derivative, and they will not be, they won't have fond memories. It's not fun, okay? And we're going to show you an easier way, but to show you an easier way, you first need to go through this passage, this rite of passage. It's important that you've done this. All right, so find the following by first principles. So they're telling you they want this using the first principles process. So for f of x equals x squared plus 2x, find f dash x, find the gradient function by first principles. Now, I'm going to let you in on a little secret. I know what the gradient function is, and I can do it by looking at it. Okay, so I know that my gradient function is going to be 2x plus 2. Okay, and you'll be able to do that in 2 days' time. All right, so you'll be able to work out the gradient function for this polynomial by sight. But this one says they want you to use first principles, and it's important that you can because it means that you get what you're doing. All right, so let's smash this out. So by first principles, what they're saying is we're going to choose a point, which is x and f of x, and also another point, x plus h, and f of x plus h. And what we're going to do is then limit that h value. We're going to get h to approach 0. So we're going to use the gradient formula, okay, or essentially use this formula here. It's the first principles formula, okay. But that's how it comes out. I hope you don't need it, but I'm pretty sure we put that on a formula sheet. Right, anyway, let's go ahead and do it. So we're going to go and put in or find out what f of x plus h, because that's what y2 is. So y2 is f of x plus h. So that's going to be f dash x, let's get our notation right, is equal to the limit as h approaches 0, just getting that off the formula there. If you scroll above, you'll see that. As h approaches 0, now let's do f of x plus h, which is y2. So we're going to go x plus h all squared plus 2x plus h. So all I've done there is I've got f of x and I've slammed in x plus h wherever I've seen x, because that's what this is telling me to do. Right, now from that I'm going to remove a function. All right, and I've just made the first of what is an absolutely bog standard common mistake that students make. When they subtract f of x, they go, yeah, take away that. But don't forget the brackets around f of x. Okay, you've got to stick that inside some brackets. Over. All right, so the formula has this as being straight over h, and the reason for that is when we do x plus h take away x, there'll always be only h left over. All right, now we've got to do some algebra. So that's going to be x squared plus 2xh plus h squared plus 2x, looking pretty nasty here, plus 2h, take away x squared, take away 2x. Now keep in mind, we'll know what the answer is, or the answer that we're trying to hit, because we'll be able to do that by sight. All right, now what chops out? So for a polynomial anyway, the highest power will always chop out. That chops out as well. And we've got 2xh plus h squared plus 2h all over h. Now, we need to write our limit in, so don't drop your limit. And what will happen if you've done this correctly is that h will always factor out. Okay, so we're going to go limit as h approaches 0, h, 2x plus h plus 2 over h. That cancels that out, which means that we don't get the divide by 0 error when I try to throw h approach 0 in there. Now let's let it approach 0. That chops that h out, leaving us with 2x plus 2, which is our derivative function. Right, so I knew that would be the answer, okay, but that's using first principles to get that answer. All right, and the last one, let's do this one here. So again, I'm going to grab a point x and f of x, and another point, x plus h, and f of x plus h, and I'm going to let h approach 0. That is, the distance between this point and this point approaches 0, i.e. I get the instantaneous rate of change. All right, so let's set it up. My derivative, my gradient function, is going to be f of x plus h, so that's my y2. This is my y1. So I'm going to drop x plus h in there, so it's 2 take away x plus h all cubed. That sucks. I hate expanding perfect cubes. Take away 2 take x cubed all over. Now remember, x plus h take away x. We'll chop out the x's, leaving us with just an h equals. All right, now what we've got to do is expand this perfect cube. Right, so there's a couple of ways of expanding the perfect cube, but probably the easiest one to show you at the moment is this method here, x squared plus 2 xh plus h squared. Okay, and then distribute the x first, x cubed plus 2x squared h plus h squared x. Oh my god, I do this using Pascal's triangle usually, plus hx squared. I know, it sounds like I'm making excuses. 2x plus 2x h squared plus h cubed. All right, now let's see if we can collect up anything. We should be able to. X cubed, x squared. All right, 2 take away. All right, so I'm going to slam that all into this spot. Remember, we're subtracting all of this, so we've got to stick it in some brackets. Now, I've been a little naughty here. I've forgotten to put limit as h approaches 0. The limit as h approaches 0 before that. I will take a mark off for that, girls, so make sure you pop that in. Right, so you go 2 take away x cubed, take away 3x squared h, take away 3x h squared, take away h cubed, take away 2 plus x cubed all over h. Now, mind you, I know that the answer will be f dash x equals negative 3x squared. So I know that that's what my target will be. You'll know that as well. Oh, bugger. I've just forgotten to put it in again. Equals the limit as h approaches 0. All right, so there goes the 2's. There goes the x cubes, leaving us with only terms with h in it. That's what's got to happen. So it's negative 3x squared h, take away 3x h squared, take away h cubed all over h. Haven't used the limit yet. Negative 3x squared, take away 3xh, take away h squared all over h. All right, now we're at the business end. Equals, okay, let's throw the limit in, which will limit that one to 0, which chops those 2 out, which leaves us with 3x squared. F dash x equals 3x squared. So there is my gradient function via first principles, but like I said, you'll know how to get there by simply doing a technique or using a technique that I'll show you. So notation is particularly important when using first principles. Notice when you can drop the lim. So the lim has to stay here all the way through until you use it. That's the only time you're allowed to get rid of it. Okay, so just watch that notation. Step it through slowly, girls. There's 1 to 13. Some of those questions are tricky. The algebra is tricky. Okay, but this is a really important part of the process. And look at that. In the next lesson, I'm going to show you how to get the derivative in one hit. Okay, so all of this is really crucial to your understanding of calculus.